ET1 energy 60, and select a donor such a way that whose ES1 value, whose ET1 value will be in between these two only. Then only it behaves as a donor. See this one. ET1 of donor always greater than ET1 of acceptor. ET1 of donor always greater than ET1 of acceptor. It is 60 and it is 60. Matching or not? Now, ES1 of acceptor greater than ES1 of donor. Matching? Now finally this concentration is very high, this concentration is less. These two energy levels are in between acceptor energy levels. That is the first condition. Donor energy levels are always in between acceptor ES1, ET1 energy levels. Then only it is a good selection of donor. How to select a donor? How to select a donor? Donor singlet and triplet energy levels are in between acceptor, singlet and triplet energy levels. If this condition is matching, then that is an excellent selection of donor for any photosensitization reaction. So don't take whatever you want, some conditions are there. So if anything is matching in between this, then that is a good selection for any photosensitization reaction. Right. This is energy order. This is acceptor, it is donor. Acceptor, donor. So that is end of photosensitization. So that is about Jablonski diagram and about ISC, about efficient, inefficient and moderate efficient. Then how to generate a ISC for inefficient molecule by using a photosensitization. Clear? So next one, properties at ground state and exit state. properties at ground state and exit state of a molecule. What are the properties you observe common or different properties at ground state and exit state? Properties at ground state and exit state of a molecule. So first property, geometry. Geometry. So what is saying Frank-Condon principle? According to Frank-Condon principle, so geometry at ground state and exit state remain same. When geometry remains constant, what about physical and chemical property? Physical properties are also remain same. So that is the advantage of getting same geometry. Geometry at ground state and exit state remain same. When geometry remains same, physical, almost all chemical properties also remain same. Most commonly, if any molecule having same geometry, physical properties are remain same. Physical properties remains constant. Even chemical properties also constant, but most commonly we will compare with physical properties only. Especially in case of geometry constant, physical property also constant. Until and unless geometry changes, property never changes. So if you give sufficient time for any excited partner, whose property changes. Next, a chemical reaction, redox reaction. Redox reaction. What is redox reaction? Oxidation and reduction. Reduction, oxidation. See, when you take any ground state molecule, excited molecule have a high tendency to involve in redox reaction as compared to ground state molecule. Every time excited molecule can actively involve in redox reactions as compared to ground state. Okay, so redox reactions are possible at excited state as compared to ground state. Okay, right. See, redox reactions are efficient at excited state over ground state. Is it right? As compared to excited state, ground state having less efficient redox reactions. Especially in your intermediate first year, redox reactions are going to come. Stoichiometry, there you will see all these reactions only. Once if molecule is excited, it is ready to undergo redox reaction. Ion electron method, okay, acidic medium balancing, basic medium balancing, some selective methods are there in stoichiometry. So that is this concept only. Every redox reaction effective under excited state. So one example I will show. See, here I am writing 4 electrons in their ground state. Okay, now this is photochemically excited. Okay, now this is under excited state. Now what about this state? This is ground state, and what about this one? Excited state. Now my question is, I want to do redox reaction over here and here. First I want to do oxidation. So what is oxidation? What is oxidation? Gain of electron, loss of electron. Loss of electron. Oxidation nothing but loss of electron. Loss of electron. See, I am going to take 2 states, ground state and excited state. So first I am taking ground state. This is a ground state. Here already 2 electrons are there. This is energy order. Now see, I am applying ionization energy. I am applying ionization energy. Now this is excited state. Here 1 electron and here 1 more electron is there. Okay, so now this electron, if I want to remove this electron, this is at which state? Ground state. Now this is at excited state. These two states are written one more time separately. I want to remove one electron from here and I want to remove one electron from here, which is easy. This one is very easy because this electron far away from nucleus and one more free electron it is. Here it is very close to nucleus and it is a paired arrangement. So removing this electron required high IP, high ionization energy required. Removing this electron required less ionization energy. So which will undergo faster oxidation? Excited state. Removing electron from paired arrangement not easy. And one more thing, this electron present in lower energy level very close to nuclei, which means this electron attracted by nuclei very strongly. This electron moving far away from nuclei. If it is moving far away from nuclei, less IP is required. So excited state required less energy as compared to ground state. Okay, so less IP means less energy. Less energy required for removing electron means oxidation takes place very fastly. So better which state? Excited state is better than ground state for oxidation. Just listen. Everyone listen here. Now I am doing reduction. Reduction is gain of electron. I am adding electron to ground state and excited state. So whenever if I want to add electron, here already paired arrangement is there. I am adding electron into higher energy level. Which orbit I am adding electron? Third orbit. First, second, third. Okay. But where I am adding electron here? Second orbit. And see, if you add this electron, you will get paired arrangement. You are getting pair and see this orbit very close to nuclei. When any orbit very close to nuclei due to attraction, we can add this electron very fastly here. Two advantages. This orbit very close to nuclei and nuclear attraction is very over here. So that's why this electron will be added here. Paired arrangement and very close to nuclei. And this electron is single electron, and we are adding far away from nuclei, no attraction from nucleus. When attraction is very less, addition is not easy. So which is better? Adding electron in excited state is better, or adding electron in ground state is better? Excited state. So finally, final conclusion is, if you want to do oxidation or if you want to do reduction, which is the best state? Excited state. How to create excited state? How to create excited state? Photochemically. Means first you activate that molecule photochemically, then do oxidation or reduction. Clear? Clear? So that is second property, redox reactions. Then this is last property, chemical reactions. Thermal reactions are differ over. Thermal reactions are differ over photochemical reactions. So photochemical reactions are excited state reactions. Thermal reactions are differ over photochemical reactions. Thermal reactions are different, photochemical reactions are different. Photochemical reactions takes place at which state? Photochemical reactions takes at singlet and triplet. Photochemical reactions takes place at singlet and triplet state. Okay. So photochemically, how many excited states are possible? 2. S1, S2, S3, that is one set. T1, T2, T3, that is one set. Okay. So here ground state only one possibility, but excited 2 possibilities are there. Excited singlet, excited triplet. Photochemically singlet reaction is different, photochemically triplet reactions are different. So excited singlet products are differ over excited triplet partner. excited triplet product, which means 3 types of products are possible. Thermally only one product, photochemically singlet product different, triplet product is different. In singlet also S1 is different, S2 different, S3 like that. In triplet also T1 different, T2 different like that. Means our target is to generate corresponding excited state. Once if you generate excited state, your answer changes. Clear? So best example for this case is, see, when I take any diene, see this is a diene. Diene thermally a dimerization reaction is possible. This is a diene dimerization reaction, thermal. Now photochemically a normal reaction is possible. Thermally one product, photochemically other product. Photochemically 2 products are expected still. Photochemically same molecule 2 products are expected. See, if I take normal molecule, photochemically direct means what? What is the meaning of direct? Directly irradiating, is it possible to generate triplet state? No. So on that time you will get a normal product. Okay, so less than 10% of dimer. Less than 10% of dimer possible. So now which state it is? Singlet state. It is a singlet state reaction. Direct means singlet. Now same molecule, what happens? See, I am using a triplet sensitizer. Here I am using triplet sensitizer. What it means? What is the meaning of triplet sensitizer? I am not. Can I use directly light here? No. No need to use light. Triplet sensitizer, taking that light, it will convert it to T1 state. That T1 collides with this, and this is giving which state? It is giving which state? T1. From the T1 product is expected. That product is this one. This is that product. These are the answers. So what about this state here now? This is the products of T1 state. Then what about this? This is the products of singlet state. So, but these products are impossible to prepare without triplet sensitizer. That is the use of photosensitization. In your examination here, if they mention T sensitizer, then you need to write these answers. This is called 1,2 cis 1,2 divinyl. Divinyl cyclobutane. I will explain photochemistry of olefins. Now this is called trans 1,2 divinyl cyclobutane. And this is 1, 2, 3, 4. 4-vinyl cyclohexene. These are the products obtained at triplet state. These are the products obtained at singlet state. These are the product which is obtained only at thermal. Thermally this is major. Photochemical singlet, this is major. Photochemical triplet, this is major. This is major in photochemical triplet. This is major, these two major in photochemical singlet. This is major under thermal, electrocyclic reaction. It is simple electrocyclic reaction. Conrotation, disrotation in electrocyclic, that is this one. So finally what I would like to say is, generating triplet state you will get a different answer, generating singlet state also different answer. Suppose if any molecule is unable to generate triplet state, means don't think it is not possible. We can generate that molecule triplet state by using a triplet sensitizer. It will come in photochemistry of olefin, no need to worry. There I will explain with proper intermediates. Right now you need to know about what is intermediate involved in this one and what are the difference in products of singlet and triplet products. Right. See, write one point. Photochemical reaction products depends on irradiate wavelength. It is always depends on irradiate wavelength. Depends on wavelength. So based on the irradiate wavelength, your answer changes. That is the question. Always you will not get same answer. If you change the wavelength, your answer changes. So how can you came to know that which wavelength is suitable for that molecule? Right or not? See, I am taking one molecule. This molecule I am applying 175, 200, 275, 385, different wavelength I am applying. Different wavelength, you will get different products if possible. So, photochemical reaction products of any molecule depends upon irradiate wavelength. Before irradiating any wavelength on molecule, first you record the spectra of that particular molecule in UV visible spectrum. Then you will get some transitions at one particular lambda. Right? Suppose if you take carbonyl compound, two transitions are possible. What are they? N2 pi star, pi 2 pi star. So, whichever molecule, the two transitions at one particular wavelength, if it is possible, only that particular wavelength you need to irradiate. Then you will get a different products. So, before irradiating any molecule, first you record spectra of that particular molecule in UV. Wherever transition takes place, take that lambda, use that lambda on molecule, then you will get a different products. So without knowing proper UV spectra of given molecule, it is impossible to get photochemical reactions. This is a key point. This point they will ask in interviews many times. How to select lambda? You are saying that I am transferring lambda to this like. They will ask how to select lambda. Is it all lambdas are possible or not? Say no. All lambdas are not possible. Specific lambdas are possible. Then they will ask how to select specific lambda. Then you need to say, before irradiating any specific lambda, first you record the spectra of that molecule. Try to record the UV spectra. Then what is the use of recording UV spectra? you came to know the electronic transition at one particular lambda. This transition, this lambda. This transition, this lambda. If you irradiate this lambda to that molecule, this transition product is major. This transition not possible. Clear? So finally what I would like to say is, if you want to get any photochemical product for any molecule, before doing experiment or before participating in chemical reaction, first we need to do recording spectra of that molecule. Without recording spectra, irradiating wavelength it is waste of time. You will not get any product. There is a major disadvantage in photochemistry. First we need to take that sample, go to laboratory. So take the spectra of that particular sample in UV, first UV. Suppose if you are getting 10 transitions, one transition at 200, other transition at 210, other transition at 230, like that. So now first transition 200, use 200 lambda, then you will get this answer. Second transition, this answer, like that. Okay? Depends upon the lambda, depends upon transition, your answer changes. That's why photochemically many products are possible. But thermally, only one is major. See, thermal I written only one. But photochemically, this is not mine. Here one more is there. And in that also one more triplet. And here not write S2 I not written. S3 I not written. Many are possible. Clear? Right. So, first directly record UV visible spectra of sample record UV visible spectra of sample and select suitable lambda max. Select suitable lambda max for transition and reaction products. Record UV spectra of sample and select suitable lambda max for transition and reaction product. So wherever transition takes place, that lambda if you take, transition related product is major. So that is properties of ground state and exit state. This is a key point. It is one of the major drawback. This point helpful for interviews. In interviews, they will ask these points. Even though photochemistry is more complicated, why you are doing photochemical reaction? This point they will ask. Why you are doing photochemical reactions if it is complicated? Because only one reason. It will give a different product which is impossible in other cases. If that product having a broad scope of importance in universe, then we are doing photochemical reactions. If there is no use, no need to do that photochemical reaction. That's it. Okay? So, here one spectral line I am giving now. (254 nanometers) pi to pi star, N2 pi star, I am giving 325 nanometers. So this is absorption maximum, this is lambda. This is UV spectra of which one? Benzophenone. Benzophenone UV spectra this is. Benzophenone gives how many electronic transition? Total how many are possible? 6. In that 6, 4 will be removed. Only 2 possible. What are the 2? Pi to pi star at 254, N2 pi star at what? 325. First I recorded spectra of this molecule. I want to participate this molecule in photochemistry. First record spectra of this one. After recording spectra, see, then I am irradiating this molecule with a suitable lambda. I am irradiating with 254 nanometers. Then what happens? So now this molecule is get excited. Now this is get excited. Now this will reaches to singlet state. If it is possible reaches to triplet state. Now from there onwards it is responsible to give product 1. One product is possible. Okay, so what is the state of this molecule? Singlet state. Then later on see, it is also involved in ISC, inter-system crossing. Then what is your answer? It will undergo inter-system crossing. After inter-system crossing, it will reach us to triplet state. From there onwards, it will give product 2. One more product. Okay, then this is your first example. Now what is the type of transition takes place here? It is pi to pi star, which one? Pi to pi star singlet product, pi to pi star triplet product. Clear? Now one more. I don't want pi to pi star. Now I am introducing 325 nanometers lambda. 325 nanometers lambda. Then what happens? See, here you will expect a singlet state. Here this is singlet state. Here you will expect a product 3. Now from here onwards it is possible to undergo ISC. Once if it is undergo ISC, inter-system crossing, then what you will expect? Triplet state. From here onwards you will get product 4. Right? Like that we will get the answer. Okay? But see, 325 nanometers, which transition? 325 nanometers N2 pi star transition. N2 pi star singlet this product, N2 pi star triplet this product. That's why many products are possible. Now these products are depends upon irradiate wavelength. Suppose if lambda is not given, then what is your answer? All we need to write. You need to write this all, because they not mention lambda. All possible transition resultant products has been measured. Should be taken as a major products. Suppose if lambda is mentioned, based on the lambda, one is major, remaining all are minor, not exist. Only these two are possible at this lambda. Okay? Suppose if it is inefficient ISC, this is major, this is minor. Suppose if it is efficient ISC, this is major, this is minor. These two are not possible. That's why photochemical reactions are not easy, highly complicated. You won't remember how many products are possible. Many products are possible, depends on lambda. See, only 2 transitions. How many products are you getting? 4. Suppose if one molecule give 12 transitions or 6 transitions, every transition adjacent singlet is there, then many products are possible. That's why photochemical reactions never give excellent yield. Whatever yield we are getting, with that only we need to do for any particular research. Okay? Right. So that is end of properties. Pi bond is activated, where non-bonding is activated. Clear? So that is end of properties of ground state and exit state. Keep heading photochemistry of carbonyl compounds. Photochemistry of carbonyl compounds. So from here onwards important concepts are going to come. Photo reduction, pattern of Buch reaction, Norris 1, Norris 2, everything will be most important. So up to here whatever concepts we learn, that all are important for both UV as well as photochemistry. Each and every point is important. Be prepared. So now we are learning carbonyl compound photochemistry, then photochemistry of olefin, photochemistry of benzene, some miscellaneous photochemistry of some selective functional groups. Okay? Right. Write down. Saturated ketone gives 4 possible transitions. Saturated ketone gives 4 possible transitions at 155, 170, 195, 280 nanometers. These are the 4 possible transitions in saturated ketone. Sigma as well as pi. Complete I am writing. Sigma to sigma star, N to sigma star, pi to pi star, later on N to pi star. 4 I written. If you provide suitable energy. But actually how many are possible? Only 2. Last 2 are only 2. Last 2, 195, 280. So these 2 are almost all equal to low energy. N to pi star, pi to pi star. Okay. So 280 nanometers transition due to N to pi star. Mostly it is due to N to pi star transition, because most chemical reactions from 280 N to pi star reactions are efficient. More chemical reactions from N to pi star only. Okay. Excited carbonyl compound always produce singlet and triplet state. Singlet and triplet state. Okay. And in the same way they produce singlet product and triplet products. They produce singlet products and triplet products. Both products are different. Excited carbonyl compound always produce 2 states because it is efficient ISC. See why we are learning carbonyl photochemistry first. Why we are learning carbonyl photochemistry? Many applications are there in carbonyl. So in your examination also photochemistry of carbonyl, one question is compulsory. Only one reason. These are the systems acts as a photosensitizers. Efficient ISC, that is the only one reason. In interview also this question is asking. Even DL also this point is given. Okay. Carbonyl compounds are efficient ISC system. Today starting class explained. Carbonyl compound 5 minutes ISC. So itself it is giving a triplet product and itself it is responsible to generate a triplet of other partner. It is acts as a triplet sensitizer. Itself it is participating in chemical reaction. That is the advantage. So final statement is it is efficient. They are efficient ISC systems. So that's why many photochemical reactions are known. They are efficient ISC systems. This molecule can give singlet exit state and triplet exit state. So don't think that only triplet will give answer. Singlet will give answer, at the same way Triplet also give answer in carbonyl compound photochemistry. They produce singlet products and triplet products. Both products are possible. So they are efficient ISC systems. So this is called Kasha's rule. You need to remember this rule. This rule is saying that according to Kasha's rule, this is gate question. Statement they given in gate. According to Kasha's rule, which energy transition or which particular absorption of wavelength will responsible to give photochemical reaction? This rule is saying that when molecule having many transition, lower energy absorption transition or low energy absorption responsible to give photochemical reaction. If lambda is not mentioned, whichever transition required low energy, only that transition is taken as major. Clear? So which is low energy here? Low energy, 280. If number is very high, it is not more energy. Nanometer. More wavelength, less energy. So most of the cases, carbonyl give N2 pi star as major. That he want to say. Kasha is saying that if molecule having many transition, lower lambda, higher lambda like that. Whichever lambda having a low energy absorption for given any carbonyl compound, only that particular lambda absorption is taken as a major. If lambda is not mentioned. Because it is a first absorption frequency for a given organic molecule. Okay, according to Kasha's rule, lower energy absorption wavelength transition involved in photochemical reaction. That statement they given. Carbonyl compounds involve in following reactions. Involve in following reactions. First one, alpha cleavage. Alpha cleavage. This is called Nourish 1. This is Nourish 1, alpha cleavage. Then beta cleavage. This is called Nourish 2. Nourish 2. Alpha cleavage, Nourish 1, beta cleavage, Nourish 2. Then inter and intramolecular hydrogen abstraction. Inter and intramolecular hydrogen abstraction. Then this is addition of carbonyl compound and olefin. This is PB reaction, Paterno-Buch reaction. Only 3 top reactions are there. It is also important one, but in interconversion this is important one. Nourish 1, Nourish 2, Paterno-Buch reaction. One more is photoreduction. This is called photoreduction. Intramolecular and intermolecular hydrogen abstraction. This is photoreduction. It is addition, Paterno-Buch reaction, addition of carbonyl compound. CC means carbonyl compound. Every time I don't write carbonyl compound, I will write CC. C.C means carbonyl compound. Alpha cleavage is Nourish 1, N1. Alpha 2 means Nourish 2, McLaughlin, Nourish 2. Retroin reaction. This is retroin. Even Nourish 2, McLaughlin, many names are there. So here Nourish 2, Nourish 1, these two are most famous and most important reactions. And in this, stereochemistry is important. Pattern Bucci. You focus these three. Nourish 1, Nourish 2, later on pattern Bucci, then they will ask dipymethane questions are asking. Be careful with these three. These three is most important for your exam. Nourish 1, Nourish 2, PB. PB you can guess very easily. Simply cycloaddition it is between carbonyl and olefin, carbonyl and double bond, carbonyl and triple bond. But problem is stereochemistry. You will suffer with stereochemistry with PB reaction. First one, photo reduction. So first we will see photo reduction, but not Nourish 1, because some applications are including Nourish 1. If you know photo reduction, everything will be cleared. First photo reduction, then pattern Bucci, then Nourish 1, Nourish 2. That is the sequence. Photo reduction. What is reduction? What is reduction? Gain of hydrogen, loss of oxygen, gain of electron is reduction. Gain of hydrogen. If any molecule takes hydrogen, reduction. If any molecule lose oxygen, reduction. Photo reduction means photochemically they are taking hydrogen with the help of light. That is called photo reduction. So photo reduction is almost all equal to thermal reduction. Both are same. But this reduction is carried out under light. That is the difference. Okay? See, right. Gain of hydrogen or loss of oxygen by any organic molecule in presence of light. In presence of light is photo reduction. Gain of hydrogen or loss of oxygen by any organic molecule in presence of light is photo reduction. Okay, photo reduction, it is similar to thermal reduction. So what is the difference between thermal reduction and photo reduction? Thermally we are doing it is photochemical, means heat and light, that is the difference. But only thing is almost all reduction products are same. So what is the reduction product? Reduction product is pinocol or alcohol. We can say simple alcohol. Reduction product is pinocol or simple alcohol. What is pinocol? Don't say pinocol rearrangement. You are very familiar with that pinocol word, because first name rearrangement is, while started anyone, they will start with pinocol. What is pinocol? 1,2 diol. 1,2 diol is pinocol, or 1,2 ditertiary alcohol. So simple alcohol means only 1 hydroxy here, 1,2 hydroxy. Here pinocol is major, most of the cases, photo reduction. Reduction product is pinocol or simple alcohols, that depends upon hydrogen donor. So here I am using carbonyl compound plus hydrogen donor. Carbonyl compound, hydrogen donor. Here I am writing lambda, suitable lambda. So this is a lambda of carbonyl compound. Then what happens? You will get either pinocol or alcohol. Two products are possible. Even if you write pinocol plus alcohols also, nothing will happen. This is actual reaction. Carbonyl compound reacts with hydrogen donor. Without hydrogen donor, this reaction is not possible. Okay? See, I am taking a benzophenone and I am reacting with a simple alcohol. Now, this alcohol is a hydrogen donor. Now, I am taking a lambda of which one? Carbonyl compound. Then see, you will get different products here. pH, pH. Here pH and this is pH. It is one product plus it is one more product, second one. First one is this one. Second one, is it also pinocol or not? It is also pinocol. So here one more product is possible. Here OH and here one more OH. It is third product. Pinocol, pinocol, it is also three types of pinocol. It will couple with self, it will couple with self, these two couple, cross coupling. Then followed by reduction of carbonyl. Reduction of carbonyl is this, and oxidation of this will give this one. These two are called disproportionation reactions. Disproportionation means what? Self oxidation, self reduction. I will show that one. See how many products we are getting. Total, see, pinocol, pinocol, pinocol and alcohol. So this is a reduction oxidation product of this one. Now what is this? This is a hydrogen donor. Now our reactant is what? Who is our reactant? Reactant is carbonyl compound. Carbonyl compound double bond converted to single bond. Now is it gain of hydrogen or not? Here any hydrogen? No. Is there any hydrogen on this carbon? No. Now here hydrogen, hydrogen. Now it is undergoing, it is taking hydrogen or not? Is it carbonyl taking hydrogen or not? This carbonyl converts like this. So now it is a reduction. Now what about this one? It is losing two hydrogens. You are getting this one. Now what is this? This is oxidation. Then what about this one? This is reduction. These two are called disproportionation. Okay, this is called homocoupling. This is called cross coupling. I will show that later. But remember, three coupling reactions and one disproportionation reaction. Disproportionation reaction, nothing but oxidation and reduction takes place within the molecule. Kenizaro reaction is an example of disproportionation. Kenizaro. So this is undergoing reduction, this is undergoing oxidation. So we don't want hydrogen donor. Our target is what? Carbonyl compound or not? Our target is carbonyl compound. Carbonyl compound undergoing reduction. That's why it is called photoreduction. Our target is not hydrogen donor. Hydrogen donor we are adding externally. Clear? Clear? Now, keep getting characteristics of this reaction. Characteristics of photoreduction means what are the key points involved in photoreduction. Characteristics of photoreduction. First one, irradiate with suitable lambda max or suitable lambda of carbonyl compound. Reaction exit state is N2 pi star triplet. This point is given in exam. Set exam, this point is given. So what is the reaction exit state in photoreduction? N2 pi star triplet, not singlet, triplet, because they are efficient ISC. Directly they given N2 pi star singlet, N2 pi star triplet, pi 2 pi star singlet, pi 2 pi star triplet. 4 options they given. So reaction exit state for photoreduction is N2 pi star triplet according to Cauchy's rule. Okay, the lambda not mentioned, whichever is low energy, corresponding triplet is preferred. So this is set question. Even in gate also, same similar kind of question they given. I will show that question. Statements they are giving. For photoreduction, reaction exit state is N2 pi star triplet. During hydrogen transfer, carbonyl compound is at exit state, hydrogen donor is at ground state. So during hydrogen transfer, carbonyl compound is at exit state, hydrogen donor is ground state. Intermediates are biradicals. Intermediates are biradicals. Then it is a disproportionation reaction. Disproportionation reaction. It is a disproportionation reaction. Irradiate with suitable lambda of carbonyl compound, reaction exit state is N2 pi star. During hydrogen transfer, carbonyl should be at exit, hydrogen donor should be ground state. Intermediate is biradical, you need to remember this, and it is a disproportionation reaction. See, they required hydrogen donors. Without hydrogen donor, this reaction not possible. So, examples of hydrogen donor: simple alcohol, allyl carbon, benzyl carbon, and you can take amide, even amine, and you can take tributyl tin hydrate. Tributyl tin hydrate also one of the hydrogen donor. These all are hydrogen donors I will use. Many hydrogen donors are there. Excellent hydrogen donor is for typical conditions TBTH. TBTH is an excellent hydrogen donor for most of the photoreductions. Tributyl tin hydrate is called TBTH. Tributyl tin hydrate, TBTH. Tributyl tin hydrate, that is tin, SN. This is amide, benzyl carbon, amide, amine. So initially hydrogen transfer takes place at oxygen followed by carbon. So hydrogen transfer never takes place on carbon first. It will take place on first oxygen of carbonyl. Carbonyl having oxygen and carbon, hydrogen transfer first takes place on oxygen followed by carbon. Alcohol, allyl carbon or allyl hydrogen. Benzyl carbon, benzyl hydrogen. Amide, amine, tri-butyl, tin, SN, hydrogen. So initially in photoreduction, first hydrogen transfer followed by that hydrogen transfer on oxygen followed by carbon. See, molecules with pi to pi star. Molecule with pi to pi star. T1 state or inert in photoreduction. Are highly inert in photoreduction. They are highly inert in photoreduction. Some molecules are there, pi to pi star also very efficient. That molecules never involve in photoreduction. So that molecules are this one. This molecule not involved in photoreduction. This molecule also not involved in photoreduction. So this molecule having pi to pi star T1, ready to form pi to pi star T1. So if any molecule forms pi to pi star T1, they never undergo photoreduction. They require different conditions, okay, different hydrogen donor for reductions. This molecule never undergo photoreduction because for photoreduction N to pi star required, but they are efficient for which one? Pi to pi star. So they require different conditions for photoreduction. They required different conditions and hydrogen donor for photoreduction. Directly not possible, indirectly is possible. If these molecules are present anywhere, don't go for reduction. Don't go for photoreduction. They are highly inert because pi to pi star is efficient in that one, not N to pi star. N to pi star is possible, pi to pi star is possible in this too, but pi to pi star is more efficient in this one. Then last point, see, if alcohol is a hydrogen donor of, or else if hydrogen donor is alcohol of corresponding carbonyl compound, pinocol is major. When pinocol is major? Pinocol is major only when if hydrogen donor is a alcohol of carbonyl compound. If both are belongs to same family, then on that time pinocol is major. See, I am taking benzophenone, and if I take alcohol, this is that alcohol. So on that time, see, pinocol is major blindly. Here pH and this is pH and this is OH, and only one product is possible. If alcohol is the donor of corresponding carbonyl compound. See, if I remove hydrogen from here to here, if I remove this hydrogen and this hydrogen, will you get same answer? Remove this hydrogen, put a bond, will you get this answer? Say yes or no? Yes. Then that is called hydrogen donor of corresponding carbonyl compound. And if you add two hydrogens here, here add one hydrogen, here you add one hydrogen, you will get this answer. On that cases, you will get only one product, pinocol. If hydrogen donor is a alcohol of corresponding carbonyl compound, on that time pinocol is measured. Over. Now see the mechanism. So that all characteristics you will understand by using this mechanism. See, I am using benzophenone at S0. Then lambda I am using. So it is a lambda of benzophenone. Then what happens? This benzophenone excited or not? So it is initially reaches to singlet, followed by IST, intersystem crossing. It will reaches to what? It is triplet. This is T1. So what kind of singlet? It is N2 pi star or pi 2 pi star? N2 pi star singlet. Then followed by N2 pi star triplet. Okay. Now I am using a hydrogen donor. This is that hydrogen donor having two methyls. Here one methyl, here one methyl. Now see, this bond is going to break, this is going to break. See, between carbon hydrogen, oxygen hydrogen, which bond is weaker? Carbon hydrogen. Less bond dissociation edge is required. So almost all, this carry 375 kilocalorie per mole. Carbon, hydrogen, and here see, this required nearly 415 kilocalorie per mole. So which energy is less? Carbon, hydrogen. Now this hydrogen is transferred because low energy to oxygen. Now what is the state of this one? Ground state or excited state? Excited triplet. Now what about this one? Ground state. Then what happens? See, hydrogen transfer takes place from here to here. This is called hydrogen transfer. Okay, so when hydrogen transfer takes place, pH, and here you may get one hydrogen and this is radical. It is at excited state. Then what about this one? This is carbon and here it is OH and this is radical. Can I? So now this is intermediate in this reaction. What is that intermediate? These intermediates are biradical. See the statement. So during hydrogen transfer, this is at excited state, this is at ground state. intermediates are biradical. Then what happens, see, this is taking hydrogen, this molecule taking hydrogen. So this is called reductive dimerization, otherwise reductive coupling formation. Okay, so reductive dimer. What is a reductive dimer? pH and here OH and here OH, two molecules. So this molecule combined with same molecule, that is called reductive dimer. Why I am saying reductive? Initially this oxygen no hydrogen, right now it is gaining one hydrogen. Gain of hydrogen is what? Reduction. Then it is undergoing dimer, reductive dimer. Okay, next possibility. Now this is initially hydrogen is there, it is losing hydrogen. So now this is oxidative dimer. Oxidative dimer, also called oxidative coupling. Many names you can use. Reductive coupling, oxidative coupling. So what is oxidative coupling product? Here carbon OH, CH3 and carbon having OH. Can I write one more CH3 and CH3? That is the answer. Okay, this is reductive coupling, oxidative coupling. Then one more is there, cross coupling. Cross coupling. This is called redox coupling. One is reduction, other is oxidation. They are coupling. Okay, oxidative, reductive dimer. Many names are there, don't need to confuse. Oxidative, reductive dimer or redox coupling. These two are coupling. When these two are coupled together, then what is your answer? pH and carbon having OH, and here what is present? CH3 and here one more CH3. Reductive coupling, oxidative coupling, redox coupling. Then this will undergo one more. See, if this hydrogen transfer from here to here, this hydrogen transfer from here to here. Okay, so this carry one radical, this radical, this radical. What is your answer? Carbon carry double bond O or not? And what about this? CH3, CH3. Then this hydrogen transfer from here to here. Then you will get OH. Can I write one more pH? Now this hydrogen, two hydrogens are there here. Now this is gain of hydrogen. What is this? Gain of hydrogen is what? Reduction. Here loss of hydrogen. Now it is oxidation. So now these two are called disproportionation reactions. These are the key points. Names are very, very important. Reductive coupling, oxidative coupling, redox coupling. Otherwise you can write dimer. So dimer means same molecule you can write. Better you write coupling, cross coupling or redox coupling. In place of dimer also use coupling reaction. They are coupling with each other. Write down. It is also called homocoupling. It is also homocoupling. Homo means same molecules coupled together. Two molecule couple, two molecule couple, these two will couple. All are pinocols only. Maximum photo reduction will give pinocols. So whichever having low energy, bond dissociation takes place and that hydrogen transfer to corresponding oxygen. See one point I given. After disproportionation, next point is hydrogen donor point I given. After hydrogen donor point, one point I given. Hydrogen transfer to excited carbonyl oxygen followed by carbon. See first this hydrogen transfer to oxygen. Later on this oxygen hydrogen transfer to carbon. First hydrogen transfer to where? This hydrogen transfer to oxygen or carbon? Oxygen. Later followed by carbon. First it is transferred to oxygen, then later it is transferred to hydrogen. Two hydrogen transfers. First hydrogen transfer on oxygen, second hydrogen transfer on carbon. Whatever points I given, that characteristics, almost all points belongs to this mechanism. So that is about mechanism. Limitations are there, photo reduction limitations, photoenol formation and some selective molecules not involved in photo reduction. That all we will discuss in your next class. Okay, we'll stop here, we'll continue your next class. So evening schedule will be announced in your WhatsApp group, and tomorrow morning there is no organic class. Tomorrow morning I am not available, there is no organic class tomorrow morning. So evening schedule will be announced later. Okay, we'll stop here.